Polymer Crystallinity by Patrick Hardy. The presentation will be over polymer forms, steps of crystallization, factors that affect crystallization, ways to control it, key temperatures, shrinkage concerns, and annealing. Crystallinity is the regular ordering of atoms in a 3D lattice. As you can see in the image in the right corner, chains are aligned in a very orderly manner, just like the socks in the image in the left-hand corner. Crystallinity is dictated by the packing of atoms and molecules, and the intermolecular forces that bind the chains. Polymers come in three main forms: crystalline, which rarely happens, which is 100% crystallinity; semicrystalline, which is 1% to 99% crystallinity; or amorphous, which is 0% crystallinity. Semicrystalline polymers have sections of chains that are in an organized manner. Characteristics include low impact strength, high tensile strength, high creep resistance, and high specific gravity, as well as higher chemical resistance and a distinct and sharp melting point. A rule of thumb is any polymer that is translucent in its natural form is known to be a crystalline polymer. Amorphous polymers contain 100% tangled chains in the polymer, which characterize them by transparency, low specific gravity, low tensile strength, high impact strength, and low mechanical resistance. They also soften over a large range of temperatures. Steps of crystallization. Nucleation, which is the seeding of spherulites, is when a center forms in which chains are able to order around. It can occur one of two ways: homogeneous, which is spontaneous and a pure polymer is required, or heterogeneous, which can form around an impurity. The second step is crystal growth. Chains begin to fold together and form ordered regions called lamellae. Lamellae grow into structures known as spherulites. The third and final step is final degree of crystallinity. There are multiple factors that affect the final degree of crystallinity. These factors include polar groups. Certain polar groups repel each other and do not let crystallization occur. Other groups are able to form crystals very easily due to the hydrogen bonding found in their backbone. A good example is polyamides. Polyamides form crystals very easily because of the hydrogen bonding between sections in its backbone. Chain length. Chain entanglement tends to occur more when there is a high molecular weight in the chains. The chain entanglement in a polymer prevents crystallinity. Another factor is tacticity, which is the way pendant groups are arranged on the backbone of the chain. Polymers can be isotactic, syndiotactic, or atactic. Isotactic is the repeating units in a single repeating manner along the backbone. Syndiotactic repeat but in an alternating manner. Atactic, there is no particular order to the units along the backbone. Isotactic and syndiotactic polymers are crystalline, while atactic polymers are amorphous. There are ways to control crystallization, including quenching or the rapid cooling of parts. Quenching depends on the glass transition temperature and service temperature of the polymer. If Tg is greater than the service temp, it will prevent crystallization to form. If Tg is equal to or less than service temp, it will only delay crystallization. Nucleation choice is another way to control it. Heterogeneous will give you a higher degree of crystallization, while homogeneous will give you a low degree of crystallization. The orientation of polymer chains is another way to control crystallization. You are able to draw out plastic material to orient polymer chains the way you want to. This is used to produce high-strength fibers and films. It is also used to produce PET bottles, mainly by the blow molding process. Key temperatures to know. Glass transition temperature, or Tg, is the temperature where plastic tends to become glass-like and brittle. The transition only occurs in polymers, and it can only occur in amorphous regions. Below the Tg, there is no molecular motion on local scale, which allows chains to move toward the nucleation center. Melting temperature is another key temperature. It is also known as Tm. It happens when the chains of polymers fall out of their crystals and ordered structure and become a disordered liquid. The higher degree of crystallinity a polymer has, the more heat required to reach their melting temperature. Above the Tm, there is no crystallization because the material is too molten and too messy. This graph shows the typical crystallization rate versus temperature curve for a crystalline material. Tg occurs before Tm, as you can see. Shrinkage in a semi-crystalline material is a large concern when processing a product, because only 85% of the shrinkage happens within 24 hours. The remainder can take up to 3 months to completely occur. This is 5 to 10 times the shrinkage of an amorphous material. Crystal formation and chain packing leads to greater shrinkage values. Shrinkage in an amorphous part occurs quickly, with 90 to 95% completed immediately after processing. After 3 to 4 hours, all shrinkage of the part is complete. Processing tolerances are easier achieved when using an amorphous polymer. Annealing can be used to fix the problem of mold shrinkage in semi-crystalline polymers. This is the processing of heating a plastic part up to half of its melt temperature for a moderate period of time before letting the material cool back down. This forces the equilibrium to where full shrinkage can take place within an hour. Annealing reduces the stress of the part, which improves the mechanical and thermal properties of the part. It is normal to anneal crystalline materials due to high shrinkage values. Annealing also improves optical clarity, surface smoothness, physical properties, and mechanical properties. Thank you.